Let us now discuss about impedance. So impedance is the ratio of the voltage phasor and the current phasor, right? But remember that this impedance itself is not a phasor. So why it is not a phasor? Because it is not a rotating vector. It is not a sinusoid. It cannot be represented in a sinusoidal form, right? But it will have a real and imaginary part. It will have a magnitude and a phase angle. Only one reason that it is not a phasor is because it is not a sinusoidally varying quantity. What is the unit of impedance? The unit is ohms, because it is the ratio of voltage and current only, which is the same as resistance. We'll now see the impedance of each of the circuit elements. So we will start with the resistance. So here we have seen that if the voltage across this is V of t and the current through it is I of t, then these both are related as V of t is equal to R times I of t. Now V of t is a sinusoidally varying component. So Vm sine omega t plus phi, let us say. Then what will be the current? Then the current I of t is equal to Vm sine omega t plus phi divided by R. Okay. Now if you are expressing in terms of the phasor, V bar we can write as Vm angle phi, and I bar, the current phasor, you can write as magnitude is Vm by R and angle is phi. So now what will be the impedance? Therefore, impedance, which is equal to the ratio of the voltage phasor and the current phasor, you are going to get Vm angle phi divided by Vm by R angle phi. So what you are going to get? R angle 0 degrees. Because in numerator also you have phi, here also you have phi. Phi minus phi you are going to get 0 degrees. If it was multiplication, then you have to add the phases. If it is division, you have to subtract the phases. Okay. Therefore, for a resistor, the impedance is equal to R angle 0. That means it only has a real part. It doesn't have an imaginary part. Next, if you take the inductor. So here, what is the relation between V of t and I of t? The inductance is given by L, and we know that V of t is equal to L di by dt. Since it is easier to differentiate, let us take I as a sinusoidally varying component. So that means if I of t is equal to Im cos omega t plus phi, then what will be the voltage? V of t is equal to L times d by dt of Im cos omega t plus phi. So what you're going to get here? Minus omega L times Im sine omega t plus phi. Okay. So here we have minus sine theta. So that means we can represent as omega L times Im cos of omega t plus phi plus 90 degrees, because cos 90 plus theta is equal to minus sine theta. Okay. So why did we do this? Because in order to represent in the phasor form, we don't want a negative maximum amplitude. We want to represent in positive form. Okay. And we have to do the required changes in the phase. Now in order to find the impedance, we have to represent in phasor form. So what will be I bar? This will be equal to Im angle phi, and the phasor, voltage phasor, is equal to omega L times Im angle phi plus 90 degrees. Okay. So from here you will get, therefore, impedance is equal to, Z is equal to V bar by I bar, which is equal to omega L Im angle phi plus 90 degrees divided by Im angle phi. So what you're going to get? Omega L angle 90 degrees, or we write as J omega L, because J is equal to 1 angle 90 degrees. So what is the impedance of the inductor? Z is equal to J omega L. You can see that this is purely imaginary, whereas in the case of a resistor, the impedance was purely real. Now finally, if you consider the capacitor. So what is the capacitor voltage and current relationship? So here we can take I of t is equal to C dV by dt. Okay. In this way differentiation we can choose. Now we have to take V of t is equal to some sinusoidally varying component. So if you take V of t is equal to Vm cos omega t plus phi, then what will be the current? I of t is equal to C times Vm into minus sine omega t plus phi. In a similar way, just like in the previous case, minus sine theta we can write as cos 90 plus theta. So what you're going to get? Omega c Vm cos omega t plus phi plus 90 degrees. Okay. So from here you can write the phasor form. V bar is equal to Vm angle phi and I bar is equal to omega c Vm angle phi plus 90 degrees. Therefore, impedance Z is equal to V bar by I bar, which is equal to Vm angle phi divided by omega c Vm angle phi plus 90. So you're going to get minus j by omega c, or you can also write as 1 by j omega c. So here also you can see that the impedance is a purely imaginary quantity, just like inductor. This is purely imaginary. Now if you come back to the impedance, I have already told you it will have a real and imaginary part. Okay. For example, if you take a resistance in series with an inductor, then what will be the impedance of this combination? Z is equal to, here if resistance is R and inductance is L, Z is equal to R plus j omega L. Similarly, if you have a capacitor, then what will be the impedance of this? Z is equal to R minus j by omega C. Okay. In this manner, you can have any combination. You can even have a capacitor here. Then what will happen? Minus j by omega c will come. Okay. And you can have parallel combinations as well. So the point is, whenever you have impedance, you can take it like it will have a real part plus an imaginary part. And the real part will be the result of some resistance, because only the resistance will give you a purely real impedance. And the imaginary part is going to be because of a capacitor or inductor. And this is called as reactance. Okay. So Z is equal to resistance we represent as R and reactance we represent as X. So this is the general expression for impedance, where R is the resistance and X is the reactance. Now what about the magnitude and phase form? So the magnitude is given by mod Z we write as the magnitude and angle we write as phi. Now what is the relationship between this mod Z, R, X and phi? Okay. So this is given by mod Z is equal to, you can write where mod Z is equal to root over R square plus X square, and phi is equal to tan inverse, the imaginary part is the reactance divided by the real part, which is the resistance. Okay. So this you can get if you know the resistance and the reactance, then you will get in the magnitude and phase form. Then if you want in the opposite direction, that means you have this, then how to get the resistance and the reactance values? So we will take this as form 1 and this as form 2. So this is the conversion from form 1 to 2. Now we want from 2 to 1. Okay, so that means form 2 is given, how to get the form 1. Okay, so here R is equal to mod Z cos phi and X is equal to mod Z sin phi. In order to visually represent this, we often make use of the impedance triangle. So the impedance triangle is a right angle triangle whose base is the resistance R, whose height is the reactance X, and the hypotenuse is the magnitude of the impedance. Okay. Then what is this angle here? This will be phi. Now the reactance X you can also write as the inductive reactance minus capacitive reactance. So why we are assigning negative sign to capacitive reactance? Because if you remember, for an inductor the impedance we got as j omega L, and for a capacitor we got the impedance as minus j by omega c. Okay. So this is because of this. So you can write here, this is inductive reactance and this is capacitive reactance. And the imaginary part, if it is less than 0, if imaginary part of Z is less than 0, this means that the capacitive reactance is greater than the inductive reactance. In such a case, we call it as a capacitive circuit because the capacitive reactance is dominating the inductive reactance. What about the case when imaginary part of Z is greater than 0? This means XL is greater than XC and it is called an inductive circuit. Another parameter is the admittance. This is represented as Y. This is also not a phasor, but it will be the ratio of the current phasor and the voltage phasor. Or this means that it is the inverse of impedance. Now this admittance is represented in terms of its real and imaginary parts as G plus JB. Okay. So what is this G? How it is related to resistance and the reactance? Okay. Before that, G is called as conductance and B is called as susceptance. What is the unit of admittance? The unit of admittance will be 1 by ohms, which is mho or Siemens, right? The same unit as conductance. So this is represented like this is represented like this. Both represent the same unit only, which is the admittance. We will now see how the admittance G and B are related to the actual components, that is resistance R, inductance L and capacitance C. Okay. So we know Z is equal to R plus JX. Okay. Where X is equal to XL minus XC, which is omega L minus 1 by omega C. Okay. Now what is impedance Y? Y is equal to 1 by Z. So this we can write as 1 by R plus JX. So if you multiply and divide by R minus JX, then you're going to get R square plus X square in the denominator. So now you can separate into the real and imaginary parts. Then what will you get? The real part of Y is equal to R by R square plus X square, and the imaginary part of Y is equal to minus X by R square plus X square. So this is nothing but the conductance G and this is nothing but the susceptance B. Now if you remember back when we were discussing about the resistive circuits, I told you that the conductance is equal to the inverse of resistance. But you can see that conductance is actually equal to R by R square plus X square. So which expression is correct? Both are correct. So why is that the case? If there was no impedance, that means there is only R, X is 0, then what will happen to G? G will be equal to 1 by R. Okay. So this is the point here. Therefore, G is equal to 1 by R only for resistive circuits when there is no impedance. So for admittance also you can draw the triangle. The admittance triangle will also be a right angle triangle. What will be the base here? The base here will be the conductance G. The height will be susceptance B, and the hypotenuse is going to be the admittance Y. Now what about each individual circuit element? What will be the admittance of each individual circuit elements? We have seen the impedance of each element, right? If you consider a resistor, then the impedance is simply Z only. Then what will be the admittance for only resistor? 1 by R. If you take an inductor, then what will be the impedance? J omega L. Okay, and admittance is 1 by J omega L. Remember, we are talking about the admittance when only inductor is present. Okay. Then similarly, what about capacitor? For capacitor, minus J by omega C or 1 by J omega C, right? So admittance is going to be J omega C. So this is the admittance for each of the individual circuit elements.